In this fourth video for Chapter 9, we're going to determine a way to find infinite series that define some of the most important functions we use, such as sine x, cosine x, e to the x, and ln x. So let's start with the assumption that we can write a function as an infinite series that we could also call a power series that looks like this: a0 plus a1x plus a2x squared plus a3x cubed, a4x to the fourth plus dot dot dot. So it's called a power series because it has powers of x in it, and it also has coefficients of the x variables tagged by the power of x. So if we're trying to figure out how this power series would correspond to the function, let's notice that if we plug 0 into the function, we get out a0, because all of the other terms are going to be 0. And let's also note that if we take the derivative of the original function, we get what? F prime of x. The a0 goes away, the a1 is by itself, 2a2x squared. We bring the power down, reduce the power by 1, 3a3x squared plus dot dot dot. And if we plug 0 into that, we get a1, and let's see if we can notice a pattern in what happens when we put 0 into successive derivatives. So if we take the second derivative, let's do that on this blackboard so we can see where it's coming from what's above. So the a1 goes away, we bring the power down, we get 2a2, and then 3 times 2a3 x to the first plus dot dot dot. So f double prime of 0 is going to be 2a2. And then let's continue this on the next blackboard. So f triple prime of 0 is going to be 3 times 2a3, and can't we see from what's coming up next that f4 of 0 is going to be 4 times 3 times 2a4. So can't we generalize this and say that f sub n of 0 is going to be what, n times n minus 1 times n minus 2, etc., or, right, what we have here, this is 4 factorial, this is 3 factorial. On the preceding page we had 2 factorial, so f, the nth derivative at 0 is going to be n factorial a sub n, right? Fourth derivative subscript 4, third derivative subscript 3, etc. So here is our formula for f, the nth derivative, that we want to solve for a sub n, and when we do that we get what? F n, the nth derivative evaluated at 0, divided by n factorial. So this here is the key that we need, so when we go back to our assumed form, we now have a definition for all of these coefficients, a1, a2, or a0, a1, a2, a3. So let's apply this result that we know how to get the coefficients, and do that for the sine function. right? So I've filled in here what happens since the process repeats. So f, f prime, f double prime, f triple prime, f4, which is repeated again, then f5, f6, f7, f8, f9, etc. So what does sine x become? So it's a0, which would be the f of 0 over 0 factorial. Remember, 0 factorial is defined to be 1. So it's going to be 0, and then the next one is f is a1x. a1 is 1, right? And divided by 1 factorial, so that's just x. The next term is here in the numerator, which is 0 x squared. The next term is here, minus 1, and that is the third term, so it's divided by 3 factorial, and it's x cubed, and the next one 0 plus x to the 5th over 5 factorial plus 0 minus x to the 7th over 7 factorial, etc. So I'm going to write this out a little more carefully on the next blackboard where we have more room. So here we have the sine x series matched up with its a0 plus a1x format. Back here we found out that the derivatives alternate between 1 and minus 1 for the odd terms, right? This is the term 1, this is the term 3, but the even terms are all 0. And so right here are all of the zeros for the even terms, and here are the odd terms alternating with the coefficient of either 1 or minus 1. So here we have sine x written out to its 11th power term. In the book on page 201, you see that if we use this version of the sine series here out to the 11th power of x and find sine at 1, we get accuracy is accurate to the 10th decimal plate. And so this is what your calculator does when you want to find the sine of a number or the cosine of a number. It's got hard-coded into it a series expansion that would probably go out one or two more terms than this, so it's a little more accurate. And you can see without too much difficulty, I would hope that if we went through the same process, we could get a series for cosine, but the alternating nature of it is going to be on the even powered terms. And we also, I think we'll reserve for class what e to the x looks like, but of course the nth derivatives are all going to be 1, and so all of the terms are going to show up. And so let's just say it starts off like this, and leave it as a mystery, or let you figure out what the rest of them are. It's actually not that difficult to do. On page 203, we in example 1, we find the Taylor series for y equals ln x. The process of doing this is a little more difficult than for sine, cosine, or e to the x, and the series converges actually a lot more slowly. We'll take a look at that in the classroom, although that's a little bit more too complex for a test question. So this is going to conclude this video on how to find infinite series for common functions. with this example for sine, and showing how we could get justifying that we could get it for cosine and e to the x using a pretty easy process, as easy a process as it is for finding it for sine.